In this video, I'm going to demonstrate finding the absolute maximum and minimum values of a function involving the natural logarithm. The function I'm going to work on is f of x equals ln of x divided by x squared. The domain is restricted to be the closed interval from 1 to 2. If you're fuzzy on this, go back to section 3.5 and review how absolute maximum and minimum works, and then come back and look at this video again. Now, a couple of things about this. Remember that the natural logarithm itself has a domain restriction. ln is only defined for positive numbers. So that means that the formula for f only makes sense for x greater than 0. Likewise, division by 0 would be a bad thing. So that means that we can't include 0 in the domain. So it's a good thing that the domain that we've been given is consistent with all of that, and as long as x is here between 1 and 2, we won't have any problem evaluating ln of x over x squared. So let's take a look at this, and so take a minute, pause the video, and give this a try. Okay, first step is that we need the derivative. Since we're still getting the hang of derivatives of functions involving ln, I'm going to go through this pretty carefully. Looking at this formula, do you see the structure, the algebraic structure? What is the outermost operation? It's actually the division. The logarithm function happens early, the exponent happens early. The last thing you do is the division. So let me get rid of some of this noise and just write in this thing. So that means that we will need the quotient rule. The top is ln of x, and the bottom is x squared. Derivative of the top. Well, what is the derivative of ln of x? It's 1 over x. And for the bottom, what is the derivative of the bottom? Two x. We now need to use the quotient rule to put all of those parts back together. Okay, so remember how this works. We need the derivative of the top times a copy of the bottom. So 1 over x times x squared minus copy of the top times the derivative of the bottom. So ln of x times 2x, whole thing over the bottom squared. So that's x squared squared. Since we're going to be doing more with this function, I suggest that we clean it up and simplify it as much as possible. There's a couple of things we can simplify. Looking in the top, to the left of subtraction, we have 1 over x times x squared. We can simplify that, and the result is x. Then we subtract, and well, not much we can do with the cluster of factors after the subtraction. like I mentioned in a previous video, it's just sort of aesthetically more pleasing to put the 2x to the left of the ln. It's just style. And then finally, we can simplify the denominator. How does x squared squared simplify? X to the fourth. Like I said, we're going to do some other stuff with this derivative, so I suggest let's simplify. Looking at the top, you can see that we've got a cluster of factors, subtraction, and another cluster of factors. And I call this a cluster of factors even though it's just x. It's just one factor, but you get the idea. There's actually an x on the left and an x on the right. That means we can factor out an x. That's an ugly x. Let's try that again. X. Okay. What's left? Okay. From over here, well, there aren't any other factors, but I still need something here, so it has to be a 1. That way, if I wanted to, I could distribute back out, and the x times 1 would recreate that x. What about over here? I need to bring down the 2 and the ln of x, like that. Now that we've factored, there's a factor on top that we can cancel with a factor on bottom. Both top and bottom have factors of x. So let's cancel an x. That will leave us with f prime of x equals 1 minus 2 times ln of x divided by x cubed. Okay, that's about as simple as that's going to get. Now think about where we were with this. We're looking for the absolute maximum and minimum values of a function. That means that we need to find critical numbers because those are candidates for the absolute maximum and minimum. Well, how do we find critical numbers? Well, you set f prime equal to 0 and solve. Okay, 1 minus 2 times ln of x divided by x cubed equals 0, and now we have to solve. We've solved equations involving fractions equal to 0 before. The trick to remember is that if the result of division is 0, then the numerator must itself be 0. Another way to see that is that we could multiply both sides by that x cubed. If it helps, you can make it x cubed over 1. And now that x cubed cancels with the 1 in the denominator, and we will be left on the left with just 1 minus 2 ln of x equals, well, what's left on the right? 0. Remember, 0 times anything is 0, even 0 times x cubed. Now that we've got 1 minus 2 ln of x equals 0 to solve, this is starting to look a little less intimidating, because now there's only one place where there's an x. That means we should be able to solve this by peeling the onion. So give that a try. Okay, what we need to do is first move the 1 over So we'll subtract 1 from both sides. Now we need to move the minus 2 over, but the minus 2 is multiplying ln of x, so we need to divide by ln of 2. That will leave us with ln of x equals, well, it's negative 1 over negative 2, but we can do a double negative simplification and just make that 1/2. Now, do you remember how to solve an equation like this? How do you undo ln? You need to use its inverse function. And the inverse function for ln is e to the x, well, e to the power. So what I need to do is write e to the left equals e to the right. The left is ln of x, the right is 1/2, and the whole 1/2 has to be up there in that exponent. Don't let it sag. And the point of doing that is that over here, e to the ln of something simplifies to just the something, and we're left with x equals e to the 1/2. In case you're wondering, you can use your calculator to do this and find out that e to the 1/2 is approximately 1.65. Now remember where we're going with this. We need to find the absolute maximum and minimum values of this function on that domain. The critical number we found, is it in the domain? It is. 1.65 is right there, close to the middle of that interval actually. So that critical number is a candidate for local maximum or minimum. Now we have to check the candidate points. Remember, there are 3 of them. We have to check the left endpoint of the domain, f of 1. We have to check the critical number, so that's f of e to the 1/2. And then we have to check the right endpoint, which is 2. We're looking for which of these y coordinates is the highest, the greatest, farthest up, and since we're looking at y coordinates, we need to use the original function f. Okay, for f of 1, I need to calculate ln of 1 over 1 squared. Well, that's actually easy to evaluate. Do you see what it is? Ln of 1 is 0, and then 0 divided by 1 squared is 0. So there we go. F of e to the 1/2 is a little bit more difficult. You can just plug this directly into the calculator. Let me point out that the numerator simplifies. How does the numerator simplify? It simplifies down to just 1/2. The denominator also simplifies actually into just e. And using the calculator, you can compute that this is 0.183, well, 0.184. Finally, f of 2 is ln of 2 over 2 squared. And this, there's really not much you can do other than type it into the calculator, ln of 2 divided by 4, and the result is 0.173. The problem didn't say specifically how many digits to keep. 3 or 4 is usually safe. Okay, so we now have three y coordinates. There's one, there's one, there's one. We have three y coordinates. Of these, which one is the greatest? That's the 0.184. So that is the absolute maximum value. Which of these three y coordinates is the least? The 0. That's the minimum. Okay, so let's write this out. The absolute minimum value is f of 1, which is 0. The absolute maximum value is f of e to the 1/2, which is approximately 0.184. Now, if you wanted to use the calculator to verify this, let me show you a way to do that. So first, there are some calculations that I just did. I'm going to go to the y equals screen now and type the original function f in as y1. So I'll hit alphabet and that key to get a fraction, and I need ln of x divided by x squared. For the plot window, I'm going to use xmin equal to 1 and xmax equal to 2 because that's the domain that we were given for this function. For ymin, let me give it, say, I don't know, negative 0.05 to 0.2. The reason for that is that if you look back at our absolute maximum and minimum calculation, we found that the absolute minimum value was 0 and the absolute maximum value was 0.184. So by going a little bit below the 0, that's the negative 0.05, and a little bit above the 0.184, that's the 0.2, that should give me a good picture of the whole graph on this domain. And yeah, 0.1 is probably okay for the y-scale. So now we'll hit the graph button and see what we get. Okay. If I hit the trace button, now I can type in values of x. If I type in x equals 1, that hops me over here, and you can see that that's clearly the minimum value of y. If I type in, yeah, this is going to be pretty here, e to the 0.5, that hops us to the middle, and you can see it's pretty convincingly somewhere around the top there. There's our 0.183, well, 0.184. And if I type 2, that's the right endpoint, and you can see that at that point, the graph has started to decrease again. Now, just so that it's clear, the absolute maximum ought to be somewhere in there. It's not exactly clear which pixel is closest, and even then we'd only get an approximation. So it's good that we have these algebraic techniques for finding an absolute maximum and minimum value. So again, here is the problem, and our final result is right there.